Namaskar and hello, welcome back to this series of lectures on concrete engineering and technology, where we are trying to study the fundamentals of concrete once again in the light of developments that have taken place in the last 15-20 years. We are trying to understand better the concepts in proportioning of concrete mixes, stages in concrete construction, special concretes, mechanisms of deterioration in concrete, reinforcement in concrete structures and their maintenance. So, in the last couple of discussions we have focused on special concretes, and within that mass concrete was the focus of discussion in the last class. Now, before we proceed in our discussion on this subject today, let us recapitulate some of the things that we did last time. Last time the focus was on revision of fundamentals from the point of view of mass concrete. We tried to understand some basic processes in modeling mass concrete and also some options which were available with us in terms of working with mass concrete. So, going over these once again quickly, as far as the fundamentals are concerned, we saw that there was no basic definition or no watertight definition that this is what is mass concrete. It is any concrete that requires a special attention to take care of thermal stresses that may arise in concrete due to the liberation of heat of hydration of cement and the ensuing volume changes. And therefore, the situation of mass concrete could arise in cases where there are large pores of concrete with relatively small surface area, and gravity dams can be cited as an example of such construction. It could arise in situations where the pores are medium size, but the concrete is high strength, which entails that the cement content will be high and therefore, the amount of heat liberated is going to be large. As far as thermal stresses are concerned, we said that these are the stresses generated in concrete on account of shrinkage and volume changes related to the release of the heat of hydration in cement. We once again saw the composition of cement in terms of its solid complexes, and all these solid complexes, they have their own rates of hydration, their own heat of hydrations that they liberate while they hydrate. And we also know that C3A or the tricalcium aluminates is the largest single compound contributor to the evolved heat, followed by C3S and C4AF, which are more or less equal, and then finally C2S. We have also seen that C2S hydrates and hardens rapidly and is largely responsible for the initial set and early strength in concrete, and C3S hydrates and hardens slowly and is largely responsible for the strength beyond 1 week. So, depending on what kind of concrete we are talking about, we need to control the chemical composition of cement. If it is high strength concrete, we need one type of cement. If we want really low heat of hydration cements from an early strength point of view, or from a mass concrete application with large volumes where strength is not really a consideration, then we need a different chemical composition. So, the whole definition of low heat of hydration cement comes into question, and we have to appropriately define it depending on the kind of use that we want the cement or the kind of function that we want the concrete to discharge. This is a summary of what fundamentals that we studied last time. Hydration of cement is a highly exothermic reaction. The heat liberated causes the temperature of the concrete to rise unless we are able to remove the heat from the body of concrete very quickly. We should remember that concrete is cast against formwork, and very often we have lifts of concrete where a fresh batch is placed against another one, which could be a previously placed layer of concrete or against rock or ground or whatever it is. Strength development in concrete is a gradual process and is intrinsically linked to the hydration of cement, and thus the properties of concrete at early ages change rapidly. And therefore, if we are talking about considering or studying the effect of a certain property of concrete, then we should really take into account the time dependence of that property, especially in the early stages. and that is where mass concrete considerations are very important. Depending upon the geometry of the member or the portion of concrete being cast, the temperature of the core of a large concrete block will be higher than the portions close to the surface, and the difference in temperatures of the core and the portion close to the surface sets up thermal gradients, which are the root cause of thermal stresses. We had gone over this example where we had looked at a block of concrete measuring 2 meters by 2 meters by 2 meters and a thin slab of 200 thick and measuring about 6.3 or 6.4 meters square, and tried to understand how the same amount of heat liberated can be taken care of or dissipated from the surface areas of these two cases. And the surface area we saw in the case of slabs is much larger than that of the cube. We had also discussed that these concretes are cast against a certain previously placed concrete at the bottom, and then there is the formwork which is there at around this block, and this surface is exposed to atmosphere. So, depending upon the exposure conditions, how the dissipation changes or the characteristics of dissipations change depending on the characteristics of the surface or the boundary conditions of the surface. We had also studied a schematic diagram like this, where we had discussed that if a concrete is cast with an original length of L, which is shown here, and the temperature rises, there is a free strain in case the degree of restraint is 0, that is something like concrete being cast on a glass plate, that is what we had talked about. Against that, if the degree of restraint is 1, that is, it is completely restrained, then this entire free strain becomes restrained strain, and the concrete does not expand beyond this point. Similarly, if there is a partial restraint, then we can have a combination of a certain amount of restrained strain and a certain amount of free strain, and depending on the ratio of these two with respect to the total free strain, we can define a concept of degree of restraint, and if we have 0.3, then we have this to be 30% of the total strain. We had discussed this example, which was a more realistic example of a concrete block being cast against the surface of a previous concrete or a rock bed, and seen how the situation changes with little external strain and a total external strain at the time of temperature rise and also at the time of the temperature fall, that is the cooling of concrete. Having done all that, we had discussed the 3 basic processes which are involved when we model mass concrete: the heat generation or liberation, which is related primarily to the cement content and the characteristics of cement, fineness, chemical composition, and so on. We had talked about the movement of heat through the concrete through thermal gradients, and we had talked about the dissipation of heat to the atmosphere depending upon the characteristics of the surface against which the concrete is cast, the kind of formwork that is used, and the kind of curing conditions that are applied after the formwork has been removed. Ambient conditions such as wind, rain, and so on also contribute to changing the characteristics as far as the heat dissipation is concerned. So, this was our discussion as far as modeling of concrete is concerned from the point of view of mass concrete, or trying to understand the kind of temperatures that are built up on account of heat of hydration of cements. So, with this discussion, we had gone on to discuss some of the options that we have when we deal with mass concrete applications, and the bottom line was that every trick that can be used to lower the peak temperature of concrete. Basically, we had seen a diagram which said that okay, from an initial temperature the concrete temperature rises and then goes back finally to a stable value. So, whatever we can do to control this temperature rise or this peak temperature, we must try to do, and that will help us a lot in controlling the thermal stresses or the thermal strains in concrete. One of them could be reduce the cement content. Another could be replacing a part of cement with material such as fly ash, which does not liberate so much heat on account of hydration, and the secondary hydration processes in the case of pozzolanic reactions with fly ash and so on. Use low heat of hydration cement. If we reduce the amount of heat that is generated from the cement by changing the chemical composition of the cement, that helps. We should try to pay special attention to the properties of coarse aggregates, the size, the mineralogy and the gradation, because all these properties contribute to the properties of concrete. And when it comes to modeling of thermal stresses, then properties such as the thermal expansion of concrete or the modulus of elasticity, they all depend heavily on the properties of coarse aggregate, and we do not really bother about them in normal construction, but as far as modeling for mass concrete applications is concerned, they become very important. We should use as stiff a concrete as possible, because if we use stiff concrete, basically what we do is reduce the water content, and if we reduce the water content, by definition or by simple arithmetic, we reduce the cement content, and that contributes to the reduction in the amount of heat that is generated. We should actually consider alternative methods of placing and compaction using roller compacted concrete, or roller compaction is a process by which we can reduce the layer thickness. So, instead of casting concrete blocks of large thickness, we can consider the option of casting concrete in layers, and that is what is the technology of roller compacted concrete construction. Given the volumes involved, all these measures help us greatly in reducing the thermal stresses. We had talked about pre-cooling, that is the use of materials such as crushed ice, cooling of aggregates and so on, in order to lower the placing temperature. Now, how much should the placing temperature be is a different discussion that engineers need to do, but from this graph here we can see that if we are able to reduce the placing temperature this way, then the amount of temperature rise that we get for a given volume to surface area ratio becomes smaller, and that is what our target should be. Similarly, we had talked about post cooling, which involves running of cold water in a network of pipes buried in concrete to remove the heat generated on account of cement hydration and therefore reduce the temperature rise. And we had talked about how these pipes and the water running through these pipes helps us cool a certain amount of concrete around those buried pipes. Having said all that, we were trying to discuss an illustrative example where we have this as an placing temperature, this as the amount of temperature rise. I am not differentiating between the temperature rise and the temperature fall, because the temperature rise is the rise from the placing temperature to the peak temperature. The temperature fall is the difference of the peak temperature and the ambient temperature to which it falls. So, in this case I have taken to be more or less the same, I have taken this line to be not really very different, and of course we have the peak temperature itself. So, as far as design and quality control specifications are concerned, we can talk in terms of a maximum acceptable temperature for individual materials, and that is what we can achieve, or we will have to achieve through means like pre-cooling. We could put a number like 5 degrees centigrade or 7 degrees centigrade. Similarly, we can put a cap on the maximum placing temperature, which is a function of the proportions and the temperature of the constituent materials. We can put a cap on the maximum placing temperature at say 12 degrees centigrade or 14 degrees centigrade. Continuing this discussion, we can fix or put a maximum amount on the extent of temperature rise and the drop as a design parameter. A specification can say that no more than 30 degrees centigrade or no more than 25 degrees centigrade of a temperature rise or fall should be allowed. Whatever means need to be taken have to be adopted. The peak temperature reached can be yet another design parameter, and the value such as 50 degrees centigrade could be an example. So, as a designer, a concrete engineer has various options which are available to him to specify, and then it is up to us and our innovativeness to figure out ways and means of how those targets can be achieved. Yet another parameter which is interesting is a thermal cracking index, which is what I am calling TCI. This is the ratio of the tensile strength and the maximum tensile stress of concrete at a given point in time. So, we are talking of tensile strength which develops over a period of time and the tensile stresses which change over a period of time depending on what the characteristics of the temperature rise and other properties of concrete are. So, at any instant of time, if we take the ratio of the tensile strength and the tensile stress, the maximum tensile stress in the block, then we can talk in terms of a thermal cracking index, and the higher it is, the better it is, because what a higher TCI would indicate that the tensile strength at that point in time is so much higher than the maximum tensile stress. So, if we have a tensile strength of 2 MPa and a tensile stress of 1 MPa, then our TCI will be 2, which means that we have sufficient strength to sustain or withstand the kind of tensile stresses that are formed. Now, the tensile strength for the purpose of calculating the TCI can be taken to be at the time of the peak thermal stress. It cannot be a constant, and as I have said, the TCI will be now time dependent, because that both the tensile strength as well as the tensile stress, they keep changing with time, because the temperatures change with time, the tensile strength changes with time, and therefore, the TCI is time dependent. And what we need to do is to take the minimum TCI and see whether our concrete meets the criteria that we have set for it or not. We have already studied, or we have already discussed that we would like to have as high a TCI as possible, because that will give us more cushion as far as our ability or the ability of the concrete to withstand a tensile stress. If the tensile stress and the is higher than the tensile strength, obviously the concrete is going to crack, and that is something which we want to avoid. So, that principle is what is manifested in a thermal cracking index, the ratio of the tensile strength and the tensile stress at a given point in time. So, if we look at it graphically, this is a schematic diagram showing the probability of cracking and the thermal cracking index. So, if we have a thermal cracking index of 1, that is, the tensile strength in concrete is the same as the maximum tensile stress, then the concrete is as likely to crack as is unlikely to crack. Of course, we do not know much about it, and therefore, this is taken as 0.5, whereas if the thermal cracking index becomes less than 1, it is more or less certain that the concrete will crack. If it increases and becomes greater than 1, then the probability of cracking goes down, and we are operating in this range. What we should remember is that cracking at the end of it is a very difficult phenomenon to predict, and therefore, even with a high cracking index, the possibility that we will miss out some portion of concrete which may have cracks, cannot be ruled out. And similarly, at low values of the TCI, it is not really sure that cracks will always be formed and formed everywhere, and therefore, there is a possibility that the cracks may not form, and that is why this diagram has been drawn the way it has been drawn, and the probability of cracking at a thermal cracking index of 1 has been taken to be 0.5. Now, depending upon the criticality of the structure and other factors, we can choose an appropriate TCI. So, the designer can specify a TCI that, well, for a particular construction, we want that the minimum thermal cracking index should be 1.5 or 1.7, and then the entire discussion becomes focused on whether we are able to get that thermal cracking index considering the heat generation as well as heat dissipation. It should be noted that the tensile strength of concrete varies with time and only develops gradually, and therefore, a value based on a parameter such as the characteristic strength cannot be used. What we want to say here is that whether it is the tensile strength or it is the modulus of elasticity, codes often give us these values as a function of the characteristic strength, 5000 root FCK, 0.7 times FCK, and so on and so forth. But these values are different than those that should be used for mass concrete applications, because these values which are given in terms of the characteristic strength are valid for mature concrete, concrete which has sufficiently hydrated and gained strength. What we are talking in mass concrete applications is instantaneous values in the early stages of concrete, and therefore, we need to determine these values as we go along in our discussion, as we go along with the concrete construction. Summarizing, what I would like to say is that we need to look at a concreting operation as mass concrete depending upon a combination of the geometry and the heat liberated. If the pore is large in volume, that is the geometry, there is a critical cement content beyond which the operation requires special treatment. Similarly, if the cement content is high, there is a critical geometry or the volume beyond which special treatment is required. You can obviously recognize this part as relevant for dam construction, where we have large volumes of concrete being poured. We are not particularly bothered about the strength of the concrete, 10 MPa, 12 MPa, I think these are the numbers that we mentioned last time. Similarly, as far as this part is concerned, we are talking about high strength concrete, and in high strength concrete there is a geometry beyond which special treatment is required. In the case of dams, there is a critical cement content which will make it important, or which will necessitate considerations of mass concrete to be applied. With this, we come to an end of one part of our discussion. Now, the second part of the discussion today deals with the concept of thermal stresses due to internal restraint and external restraint. Now, in the case of internal restraint, we are bothered about peak stresses being reached in a period between several days to about a week, and the central part of concrete pour reaching a maximum temperature, and the temperature difference being between the core of the concrete and the surface. In the case of external restraint, we are talking about peak stresses being reached in a period which varies from several weeks and maybe a few months. In the case of external restraint, the discussion is affected by the rate of temperature fall, rigidity of the restraining body, the length of the member, and so on. As far as cracking thermal stresses in internal restraint is concerned, the thermal stresses on account of internal restraint could lead to appearance of cracks at the concrete surface, which are either vertical or horizontal, which could be several centimeters to several tens of centimeters deep, but they are only about 0.1 mm as far as width is concerned. So, they are not very wide cracks, whereas the cracking on account of external restraint, these cracks are essentially penetrative in nature and their extent could vary with age. They sometimes cross at right angles and run right through the depth of concrete and measure more than 0.2 mm in width. In fact, you would recall the kind of cracks that we showed in an example in the last discussion, where we showed formation of cracks and we showed that those cracks run through the body of concrete. This closes our discussion on the basic theory of mass concrete, or a theoretical qualitative discussion on mass concrete. From this point onwards, what I am going to share with you is the work of a graduate student who did his thesis with Professor D.C. Rai in our institute and worked on thermal stresses in mass concrete at early ages. So, in this presentation or parts of this presentation, we would see the actual numbers that were obtained in a laboratory study, which illustrate the kind of discussion that we have been doing in terms of temperature rise, temperature fall, the temperature at different parts of the concrete, and so on and so forth. This picture shows the experimental setup which was used. This is a plain concrete block that was cast. This here is a reinforced concrete block that was cast, and this here is a reinforced concrete block cast with a sleeve, where water was run to simulate the conditions of pipe cooling or post cooling. This here is a representation of the formwork, where we used a 20 mm thick ply or a 25 mm thick ply with a 100 mm thick insulation. With these blocks, the experiments were carried out using a concrete with different concretes. Blocks which we talked about last time were cast using different concretes, and this is an illustrative example. The cement content is very large because we are trying to work with relatively high strength concrete, an M45 concrete which could have a compressive strength of about say 55, 56 MPa. So, with this high cement content, these are the kind of blocks that were cast. So, this shows the different blocks made with, or the formwork for the blocks made of plywood, and this shows the concrete that has been cast, and this here is the representation of the sleeve which was left out or not, or the sleeve which was later used for running of water pipes. Now, this is a half filled block with thermocouples being used at different places to monitor the temperature of concrete during the hydration of cement and the subsequent cooling, and here is the insulation. This is a diagrammatic representation of the different thermocouples that were used for measurement of temperature. Thermocouples were placed at the surface of each box. Ambient temperature, exposed surface temperature is also measured with the help of a thermometer. There is the center, and there is a face, there are these faces, and there is the bottom, there is the top. So, thermocouples were used to monitor the temperature at different points in the concrete, and was validated using water to give us these kind of values, which basically showed that the thermocouples were working properly, and within a range of, let us say, 0 degrees to 100 degrees, we have a reasonably accurate way of understanding or measuring the temperature. Now, after the concrete had been cast and all these thermocouples were in place with the different blocks and the different kinds of concrete, indeed the data acquisition becomes a problem. So, a data acquisition system was used, as can be seen here. Different kinds of softwares, whatever they are used in the laboratory, are used to acquire all the temperature changes or all the measured values of temperature at different locations in the concrete of the plain concrete block, the reinforced concrete block, and the concrete block with reinforcement and the sleeve that ran through it. Now, here are the results. So, if we look at the plain concrete specimen, there are different readings that we have. The peak temperature that we get in terms of hours is somewhere here, and the values range from say 60 to 70 degrees centigrade, with the ambient temperature varying the way it is shown here. Similarly, for the reinforced concrete specimen. Now, it is interesting to see that as far as the reinforced concrete specimen is concerned, the peak temperature is not very much different from the plain concrete, and that is the way it possibly should be, because the presence of reinforcement per se does not alter the amount of heat liberated. What the reinforcement does is to restrict the movement of concrete as far as expansion or contraction is concerned, but as far as the temperatures are concerned, they will still be rising the way they should rise. Coming to the temperature of the concrete specimen with the sleeve, these temperatures are 10 to 15 degrees lower than those observed in the case of plain concrete and the normally reinforced concrete, and that shows the importance of the heat being gotten rid of through the sleeve. If we look at a graphical representation of these temperatures, if we look at plain concrete, the center, the face and the top, these are the values. In reinforced concrete, these are the values, and the center or the sleeve or the specimen with the sleeve, these are the values. So, if it is interesting to see that even though in this case the center is higher than at other locations, and that is the kind of concept that we are talking of in terms of a core of concrete, here the center is at a lower value because we have a sleeve there, and that is helping us get rid of the temperatures or getting rid of the heat, which results in lower temperatures. And this is a graphical representation of the temperatures, with these temperatures being more or less similar and these temperatures being actually much lower than what is observed in the other two cases. These pictures compare the temperature histories obtained for the plain concrete, the reinforced concrete and the reinforced concrete with the sleeve. So, here we have the temperature at the top and here we have the temperature at the center for these three specimens. Similarly, in this case we have the bottom face. At the bottom face again the results are similar, and the side faces. At the side faces the difference is much smaller, because at the sides the effect of having a sleeve is reduced, but still there to cause some difference in the peak temperatures. Now, if we look at the temperature differences, then we look at plain concrete, the reinforced concrete and the reinforced concrete with a sleeve, then we find that the temperature difference is the highest. Now, having seen the experimental results, let us try to see what goes on in a numerical simulation or an analytical study of mass concrete. What we really need to solve is the Fourier heat conduction equation, which gives us how the temperature varies with time in a three-dimensional plot or in a three-dimensional space when there is a certain amount of heat generation taking place in that block of concrete. And in order to solve this equation, what we need is a lot of boundary conditions, and these boundary conditions could be in terms of the prescribed surface temperature, the adiabatic surface temperature, the prescribed heat flux, heat transfer due to convection, heat transfer due to radiation, the contact between two solids, solar radiation, and so on and so forth. So, if we do that kind of analysis, we have to understand also the material properties, and these are the kind of material properties that we need to determine in the lab. So, apart from doing the experiments with concrete specimens, we also need to understand the heat of hydration of cement, and this is the plot of the rate of heat of hydration or the rate of liberation of the heat of hydration, and this becomes an important input in our simulation exercise. Then we have been talking about the effect of the properties of rock on the properties of concrete in terms of thermal conductivity. Now, these are the values that are given for thermal conductivity in the literature. So, we can use some set of values based on the published values in literature and the kind of aggregates that we actually use in the study. We also need information about the effect of aggregate type on the conductivity of the concrete. Now, concrete needs to conduct the heat, that is, heat needs to flow through concrete, and that again depends on the properties of the aggregate, because we should remember that at the end of it, concrete has about 50 to 55, maybe even 60%. In case of mass concrete, it could be even more volume fraction of coarse aggregates. So, if the heat is being conducted through the concrete will behave as a heterogeneous material comprising of the mortar phase and the aggregate phase, and that aggregate phase will have an important bearing, or the properties of that aggregate phase will have an important bearing in determining properties such as the conductivity of heat is concerned. So, depending on the aggregate type, we will have different densities and different conductivities. We also need to have data for the coefficient of thermal expansion of concrete, and that again varies from aggregate to aggregate, and these are the data which have been obtained for different dams, different aggregate types, and are listed here. So, we can see that the difference could be as much as, let us say, 7.6 is possibly the minimum here and 13.6 is the maximum. So, it is not really twice, but it is something which needs to be kept in mind when we are doing the simulation or the analysis. The density, of course, is another important parameter, and we have plain concrete, reinforced concrete, the concrete with the sleeve in this case, and these densities also become important when we are carrying out the analysis. Experiments in this study were also carried out using small or smaller blocks with 250 mm, and there we tried to measure the temperature of concrete at the center and the surface, and given the size here, the difference is not much. It is 67.2 and 66.8 as far as the temperatures are concerned, and that is why we can call it a semi-adiabatic cube. That is not there. We do not expect much heat transfer to be taking place between the core and the surface if the temperatures are similar. Similarly, if the size of the cube is 500 mm, that is 50 centimeters cube of concrete, then the temperature difference is about 80.1 versus 77.5. So, these are the kind of data that help us better model a large pour of concrete or a larger pour of concrete which was used in the study here. If we look at the discretization and the modeling issues, this is the mesh of reinforcement which was used in the concrete. This here is the sleeve which has been kept, and this of course is the plain concrete. 4 noded linear heat transfer tetrahedron elements were used in the analysis, and these are the results that we get in terms of temperatures for the plain concrete specimens. So, this is the half space, that is the section of this cube, and we can see these temperatures 65 degrees and so on, whereas the corners here are the coolest at about 51 degrees. Similarly, for the reinforced concrete, these are the reinforcing bars that we see here, and we can see in this picture what is the temperatures of these bars and the center, the core, and so on and so forth. Similarly, for the reinforced concrete specimen with the sleeve, we have this temperature distribution, which is making it much cooler in the neighborhood of the core, and this scale is quite different. The red here is only 60.1, whereas the 60.1 kind of a number here in this picture would correspond to a green. So, one must remember that these pictures, the color itself does not have any significance unless we read what temperature the color is representing. Now, if we compare the results of the measured values and the analytical values, these are some of the comparisons that we get in terms of the plain concrete specimen. This is for the temperature at the center, the top face, and the bottom face. There are two things which we should be looking for when we are discussing these results. One is the peak temperature itself, what is the number. The second is the time at which it is reached, and of course, then we have these rates or the variations during the cooling phase and the heating phase. So, if we can see from here that the simulation or the analysis using the parameters that have been determined or used from the literature is pretty much all right as far as the rising part is concerned. It is quite all right here as far as the peak temperature is concerned. It is acceptable here perhaps, but here there is some problem. Similarly, as far as the falling side of temperature, as far as the cooling of concrete is concerned, there is some difference, and the model is giving higher values than the measured values, and that is what we need to rectify. What happens is, or what this shows, is that the parameters which were important for the dissipation part of concrete, there is some error which is creeping into our calculations, which is giving a higher result. Similarly, for the reinforced concrete specimen, or for that matter the concrete specimen with the sleeve. So, in all these cases we see that the rate of temperature rise, the peak temperature, these are fairly well represented by the model that has been used. The time at which the peak temperature occurs, that is also more or less captured, but the model that was adopted was not good enough if we are looking at the falling side of temperature, that is the cooling phase of concrete is concerned. But as far as the semi adiabatic conditions is concerned using abacus, the results are pretty much in agreement for the small specimen as well as the large specimen. The smaller specimen was 250 mm and the largest specimen was 500 mm. Moving on to the stress analysis, we need to have the modulus of elasticity which is determined. So, if you carry out experiments to determine the modulus of elasticity at 1 day, 3 days, 7 days or 28 days, these curves here gives you the stress strain of concrete, and we can see that as the age increases, the concrete becomes stiffer. And if we calculate the values of the modulus of elasticity at different points in time, we get these values in terms of MPa. So, 9,000 to 24,000, 25,000, say 26,500, maybe 32,000 at 28 days. So, there is a difference of more than 3 times, and therefore, when we try to talk in terms of stress development, we must take this into account and incorporate that in the model. So, this is the representation which was used in this model to analytically determine or estimate the values of E as a function of time using E0, E1 and E2, which are defined here, and E3, and based on that we do a stress analysis. We find these stress values which are shown in this graph. The interest or the thrust in showing these numbers or showing these graphs or pictures is not to understand the quantitative nature of the problem so much as it is to understand that yes, there is a serious amount of mathematics, there is a serious amount of modeling that goes into the process, and we are able to do it and get results which are close to that obtained in the experiments. So, if we look at the stress variation with time, we find that the stresses are varying at different nodes or different locations in the concrete block as a function of time. And this is exactly the kind of concept that we have to keep in mind when we are trying to understand whether or not the concrete will crack. If a certain stress is developed, then at that point in time the concrete should have sufficient strength to withstand that stress. So, in our discussion today, we have covered more ground on issues relating to mass concrete, especially in terms of parameters that can be used by engineers when handling such concrete, and we have discussed some results from a laboratory study to put the discussion in the first part in perspective. And before we close, as usual, let us try to see if we can understand a little bit more about the properties of concrete in the bracket of, let us say, 3 to 7 days more closely. We get information about the effect of the properties of coarse aggregate on the properties such as thermal expansion or conductivity or the modulus of elasticity of concrete, and study available or suggested methods for the estimation of temperature of fresh concrete as a function of the temperature and proportions of the constituent materials. Now, before I close, I would like to thank my friends in Kajima Corporation in Japan, especially Dr. Mizobuchi, who helped me understand this fascinating aspect of concrete engineering, and also to Piyush Raj and Professor Rai for permission to use the material from the graduate study. Thank you.